All right, what I wanted to do was go through this exam and talk to you how I would be thinking about these questions as I was going through. So I want to look at question one. You say when a methyl substituent on cyclohexane molecule will prefer to be in the blank position in order to minimize potential energy. So we've seen this several times where methyl groups like to be in the equatorial position. That's going to minimize potential energy. So here we go, equatorial. All right. So next will be which the following is a cis. Okay, so cis indicates that my two substituents, in this case carbons 1 and 2, should be pointed in the same direction. So here that methyl group is pointed up and that methyl group is pointed down, right? And they're carbons 1 and 2. So while that is a 1,2-dimethyl cyclohexane, they're trans. All right, so here this is up and that's up, and we're at carbons 1 and 2, so that's looking good. Over here on C, that one is relatively up, and this one is, well, it's hard to tell, right? Out, up, down, what is it? So if we recall, pardon me, the actual substituent here is down, therefore this one is up. So that methyl group is indeed down. All right, so on D, we have an up and an up. You're like, oh, that's cis, but look here. This one's a carbon 1, this one's a carbon 3. So the correct answer is B. All right, an sp3 hybridized carbon will have blank hybrid orbitals and blank unhybridized p orbitals. So if it's sp3, that means it's taken its s, its p, its p, and its p, and it's hybridized them all. So there are 0 unhybridized. All right, so 0 unhybridized, and all 4 happen to be hybrid. So what if I asked you sp2? I know that's not the question, but if that were the case, it would be what? It took its orbitals and hybridized s, p, and p, and it left a unhybridized p out. So the correct answer is C. All right, how many pi bonds does bisphenol S contain? So you have 1 pi bond in every double and 2 pi bonds in every triple. So no triples, but I see 1, 2, 3, 4, 5, 6, 7, 8 double bonds, and that's it. So that's going to give me 8 pi bonds. All right, which of the following acids would have the strongest conjugate base? All right, so strong acid gives me weak conjugate base. All right, so it's asking me for the strongest conjugate base. So that would be what? Strong conjugate base gives me weak acid. So I'm looking for the weakest acid here. And remember, the higher the pKa, the weaker the acid. So that would be B, right? Has the highest pKa, so that's going to be the weakest acid. Thus, its conjugate base would be the strongest. All right, there's a little bit of a formatting error here. There should have been a space between H2O and the letter B. So apologize for that. But we need to draw the Lewis structures of all 4 of these. So water, okay, oxygen likes to make 2 single bonds with 2 lone pairs. All right, oxygen here. So what we've done is we've added a proton to our oxygen. Aluminum is a group 13 atom. So they like to make 3 bonds, no lone pairs. Nitrogen is a group 15, 3 bonds and a lone pair. And carbon, of course, likes to make 4 bonds. All right, so looking at these, the central atom in water is oxygen. So that's sp3, 4 different things, 2 lone pairs, 2 hydrogens. In hydronium, it's also sp3. You got a lone pair and 3 hydrogens. Aluminum, we're sp2, right? Because we're only bonded to 3 things. Nitrogen is bonded to 4 things, a lone pair and 3 hydrogens. So it's sp3. And then, of course, carbon, sp3. All right, all four things. Okay, so then the question is, does not have a tetrahedral. So this guy being sp2, he's trigonal planar, not tetrahedral. All right, so a sigma bond can be formed from the overlap of which of the two atomic orbitals shown below. So the way I like to think about this pi, right? Pi bonds, they're going to come from two things that we've learned about, py and py overlap, right? So that's when they're side by side like this, or pz, pz. I don't know what that was, pz. All right. And that's when they're side by side as well. All right. So if you see py, py, and pz, pz, that's going to be pi. Everything else is sigma. So scanning through this, I see this guy, right? And the question is, a sigma bond can be formed from which of the following? And this is a no, right? So anything else a no? No. So the only choice that makes sense is G. Right, select the functional group that does not contain a carbonyl. Right, so this is where you got to know your carbon, your functional groups, right? So ketone, that where we have two R groups on the side for each carbonyl. So definitely carbonyl, aldehyde, R group, and a hydrogen. Amide, right? That's where we have a carbonyl adjacent to a nitrogen. Amine, okay, that's where you have an sp3 nitrogen, and it's either bonded to hydrogen or carbon, not a carbonyl. So that's a possibility. And then ester, that's where we have a carbonyl that's flanked by an alkyl group and an O alkoxy group. All right. So amine is the only correct answer here. Select the functional group below that does not contain a pi bond. All right. So carboxylic acid has a carbonyl. An alkene has a CC double bond. An alkyne has a CC triple. An alkyl halide, that's RX. And then a ketone, we saw that here. All right. So if you know your functional groups, you can kind of tack them like this, and you see they all have pi bonds with the exception of the alkyl halide. All right, secondary amine. All right, so amine is when you have an sp3 nitrogen, all right, and it's bonded to a combination of carbon and hydrogen. And if it's secondary, that means two groups are carbon and the final group is hydrogen. All right. So B and E are not correct because they are amides, right? And C is a primary amine, only one carbon group attached to the nitrogen. D is a tertiary amine, three carbon groups attached to the nitrogen. And then A, that has two carbon groups attached to the nitrogen. All right, so the conjugate acids, all right, of the following molecules. So if we take the Lewis structure of this molecule, okay, and then we add acid to it, right? Because we're drawing the conjugate acid, so we need to add H plus. So when we do that, the hydrogen gets onto the nitrogen. And now we go up by a charge of 1. All right. So acetic acid, this one's a little tricky because of the way the formula is written. All right. So you have a CH3, and then that carbon with an oxygen parentheses indicates that you have a carbonyl. All right. And then we have O, then H. So we put our lone pairs on our oxygen atoms, and it's asking for the conjugate base. So what's happening here is we are losing a hydrogen. So I'm going to write minus H plus. All right. So we lose that hydrogen. So to draw that, that hydrogen is going to come off the oxygen. We get a negative charge because we've lost the hydrogen now. All right, conjugate acid of H2S. There's the Lewis structure of H2S. Now, sulfur is a group 16 element like oxygen, so it can make two bonds, two lone pairs. And since we're drawing the conjugate acid, we need to add a hydrogen to it. And there we go. And finally, the conjugate acid of the molecule ethanol. So an acid, we're adding hydrogen. So that's going to go on to oxygen. All right, there we go. Okay. For each of the indicated atoms, sorry, typo, in the molecule below, provide the hybridization, electronic geometry, and bond angle. So if we look at sulfur first, off to the left, how many things it is attached to? 4. So it's sp3. As soon as you hear sp3, you know that's going to be tetrahedral, 109.5. All right. Same for oxygen, right? 4 things, sp3, yada yada. Right. Then carbon over here on the middle molecule, that carbon's attached to 2 things, so that's sp. So that would make it linear, 180 degrees. Right, the nitrogen over here on the left, or sorry, the rightmost molecule, it's attached to a carbon, and a lone pair. Right, so that would make it 3 things. So it is sp2, and that is going to be trigonal planar and 120 degrees. Now this one's tricky up here, this carbon. All right. The reason it's tricky is because you're kind of having to do 2 things. You're having to figure out how many things the carbon's bonded to, right? It's clearly bonded to 2 carbons, but don't forget how many bonds are explicitly shown in this carbon atom. It's got a double bond to this carbon over here and a single bond to this carbon over here. So it's a total of 3 bonds. So there's 1 more that carbon needs, and it's to a hydrogen that is assumed to be there. All right. So now our total number of things is 1, 2, 3. So that's sp2, trig planar, and it's 120 degrees. All right. All right. So atenolol beta blocker, which of the indicated H atoms would be the least acidic? Consult the pK table below and provide a brief explanation of your choice. All right. So what I'm looking at here is I've got an NH acidic proton, but it's in the amine functional group. All right. Then I have an OH function or hydrogen, and it's in the alcohol functional group. And then I have this NH here that's in an amide. So this table over here is handy because what it tells me is that the pKa for an amide is about 15.1, for an alcohol 16.5, and an amine 38. So of those 3 groups, which one is the least acidic? And that would be the amine. All right. So the amine is going to be the least acidic, or the H1 is going to be the least acidic. Okay. Major driving force behind chemical reactions, formation of the weaker base, or we could also say the weaker acids, right? So indicate which of the 2 acids below is the stronger acid. There it is. Okay. So over here, pKa 8, pKa 10, this is weaker. Holy moly. This guy is weaker. Right, has a higher pKa value. So by definition, its conjugate base is going to be stronger. So this is its conjugate base over here. So this is the stronger base. All right, but it doesn't want me to indicate which one's the stronger base. It wants me to indicate which one's the what? Weaker base. Okay, Then which side of the equilibrium is favored? It's going to be the right side. That's all falls into place once you figure out where the weaker acid is. The weaker acid and the weaker base will always be on the same side. Draw both chair conformations of cis 1,2-dichlorocyclohexane. This is something we've been doing in lab. All right. So I'm going to go ahead and just get to work here. All right, so that's C1 and C2. So here's C1 and here's C2. So what I have to do here is look at C1, and at C1 from the top view, I have chlorine pointed up. So that means I got to put chlorine up here. And then there's a hydrogen to be understood down there. Over on C2, I have a chlorine that's also up. So we got to put it up there. And then there's a hydrogen understood to be down there. So now I need to draw the other conformation. So what it's asking me to do is ring flip. So what I'm going to do with this ring flip is I'm going to pull carbon 1 down, right? And then carbon 4 back here up. So I'm going to say carbon 1's a head carbon, carbon 4 is a foot carbon. So carbon 1 is now here and carbon 2 is now here. So where's my axial on carbon 1? It's down like that. So my equatorial is up there. My carbon 2, the axial is up. And it's there. So let's see. C1, chlorine has to be up, so it's going to be here. And H is down here. And then on C2, chlorine's got to be up and H here. So I have to figure out, all right, which one has better potential energy? So on the left, right, I've got an axial equatorial. If I look at C1, C2, right, my chlorine is axial C1, equatorial C2, right? Then I go to C1, C2 here. C1, my chlorine is equatorial. And my C2, the chlorine is axial. So it's the same, right? I got axial, equatorial, equatorial, axial. So now my equilibrium constant is going to be equal to 1. E1 is equally favored. And that's kind of my explanation as to why. All right. Finally, we get to the bunny. All right. So the bunny is looking at this molecule. All right. So if we look at his little paws, all right, this is his left paw if you were the bunny, and this is his little right paw. Okay. And so what we're going to do is we're going to see what he's looking at. So off to his right, okay, is the chlorine, and that is pointing upwards. So the rest of the pieces are going to fall in. Right. So off to his left is hydrogen, and down it is below his little nose is the CH3. All right. That's a methyl group there at the end. All right, and then we're going to go to carbon 2. Then on the back, oh, wow. So this is eclipsed, all right, because off to his right again is the halogen, and then hydrogen, and then another methyl group eclipsing. So this is not the best we can do, right, because we have eclipsing methyl groups, and that's not good. So what I'm going to do is rotate that front carbon 180 degrees. And when I do that, that front carbon 180 degrees, my methyl goes from 6 o'clock essentially to 12 o'clock. Then my chlorine comes over here and my hydrogen over here. And I'm going to leave that back carbon alone. And there you go. All right. So that is the exam. All right. So, or the practice exam. So again, format will be similar in class, start up at 11 o'clock. So good luck studying tonight. Reach out if you need anything. And if not, I'll see you tomorrow morning. Good luck, everybody.